All right, well, our topic for this week is waves, and we've got several different types of waves we're going to talk about. And we actually have two chapters, chapter 10 and 11. 11 is on tides, but the tide is just a very large wave. So this will be broken up into probably um, definitely two, maybe three of these 15-minute narrated slideshows. This first one will get into waves and how they work and how they're classified and wind waves. And if I run out of time, then there'll be a second, probably shorter one on some of the larger, unusual features of waves. So let's get to the slides. Here's the first slide. Um, Obviously, we're talking about waves in the water. A wave is a disturbance caused by the movement of energy. And one of the important things to remember is that the energy is moving, and it says not the water is moving, but it's moving generally in a circle. It's what we call orbital motion. So the thing to remember about this is that the waveform moves forward, but the water stays pretty much in the same place. You'll notice in the picture here from the book, the seagull um, essentially stays in the same place. It moves around in the circle as the wave goes by. So let's take a look at this a little bit more closely. You can see some features that we're going to talk about here labeled. So the crest is the top or the high point of the wave. And there are two crests on this diagram. They're labeled A and B. And the trough is the low spot on the wave. And you can see they've got one trough labeled here. The wave height is simply the difference between the bottom of the crest and the top, or I'm sorry, the top of the crest and the bottom of the trough. But the really important characteristic we're going to talk about is the wave length, which is measured typically from crest to crest. It can also be measured from trough to trough, or really as long as you go from the same part on one wave to the same place on the next wave. But generally speaking, we go crest to crest or trough to trough. So you should know what those terms are: wavelength, wave height, and crest and trough. The picture on the right shows us what's really happening as the wave goes by. And this particular picture is of what we call a deep water wave. It's a wave that has plenty of room for motion. It's also called an orbital wave because the water particles move in a circle or a little orbit. Now you'll notice that as the wave goes by, the largest orbits are up at the surface, and as you go deeper in the water, the little circles get smaller and smaller. The base of the wave is roughly 1/2 of the wavelength below the surface. So once you get below the 1/2 wavelength distance, the motion is not significant, which means that if you're in a submarine and you're getting seasick because of that circular motion, if you take the submarine down below 1/2 of the wavelength of depth, that motion will be insignificant. And this is going to be very important a little bit later on when we look at the behavior of waves near the shore, and also when we talk about classification of waves, and how some of the really big waves behave as well. So let's take a look at the next slide, see what we've got there. How do we classify waves? Well, there are a lot of ways to do that. We can use the disturbing force, and that's really what we're going to do with as we go through this, is we're going to kind of focus on the disturbing force. That's the source of energy that creates the wave initially. We'll spend a significant amount of time talking about wind waves, because those are the waves that we see most when we are standing on the shore. Pretty much every wave you see if you stand on the coast is a wind wave. The restoring force is what causes the water to go back to being flat again. Now you'll notice on the left-hand side of this diagram it says surface tension. So water has what we call surface tension because of the attraction of water particles for each other. And very small waves are restored, or the water goes flat again simply because of surface tension. Most of the waves that we see, however, the water goes flat because gravity pulls it flat. So that's something to kind of keep in mind in the back of your head. We won't really say much more about that. But when we create wind waves, you'll see that the surface tension or capillary waves are the first ones to form. They rough up the surface of the water and then facilitate the formation of wind waves. We can also use the wavelength. This is the most useful way to measure the size of a wave. We don't typically measure the wave height. We measure, well, I mean, we do measure it. But when we're comparing waves, we typically look at wavelength. And then water depth. Water depth is important when you compare it to wavelength. And this is a very important term here. A shallow water wave is a wave that is touching bottom. So if we go back to this picture here, if the water has a depth of less than 1/2 of the wavelength, we would call that wave a shallow water wave. We're going to look at some very, very large waves a little bit later on in our discussion. And because they have a really long wavelength, they are shallow water waves even when the water is 2 miles deep. Wind waves, when they get close to the shore, become shallow water waves as the depth decreases. But the really big waves we talk about turn out to be all shallow water waves. So this is a relative classification. Deep water waves means that there's plenty of room in the water for all of this motion to occur. So a deep water wave is any wave that is in water that is deeper than half of its wavelength. And then the last classification scheme we'll mention is free versus forced. A free wave is a wave that is free to move once the disturbing force is gone. So if you throw a rock in a pond, the wave that moves away from that rock is a free wave. When the wind creates waves, they move until they hit something. So those are free waves. A forced wave, the disturbing force has to exist for that wave to continue to exist. The only forced wave that we're going to be looking at will be the tide. So, we already mentioned this wave classification by water depth. And so just to reiterate, the depth of the wave for a deep water wave has to be greater than half the wavelength. The only waves that we will discuss that fit this classification are wind waves in the open ocean. The rest of the waves that we talk about all behave as shallow water waves. This includes wind waves when they get close to the shore, and the very large waves that we talk about, like tsunamis and tides. So, the rest of this discussion will be about wind waves. Wind energy is transferred to water. That's what creates the wind wave. So there's our energy source. We begin with some little capillary waves. They form from friction of the wind over the water, and they rough up the surface, and that allows the wind to transfer more energy into the water. And that additional energy makes larger waves that we would call gravity waves, where gravity would be the restoring force. The maximum height for these waves is going to be about 1/7 the wavelength. So they can't be more than 1/7 as tall as the wavelength is long, which means the steepness is limited to basically 1/7. When these waves initially form, we have something called sea, which is all a bunch of different sets of waves mixed together. And then as they move away from the storm under which they form, they become sorted by size. The faster waves move out in front. The slower waves fall behind. The faster waves then become their own little set, and the slower waves become their own set, and they all move away. And we refer to this as swell, which is those regular waves that you see approaching the beach. During a storm, when they're all mixed up, it's C, and the stuff that comes out and becomes sorted by size and speed, that is what we call swell. The waves travel in a train. The lead wave disturbs the water. And what you'll notice on this diagram is that as the train moves forward, the lead waves, which are disturbing the water, lose their energy, and the new waves in the back kind of show up because the water is continues to be disturbed. So the wave train, that set of 4 or 5 waves, moves forward, but an individual crest within that train will appear at the back, move to the front, and then disappear. The factors that affect the growth of the wind wave, there are 3 of them. This is how we transfer energy into the water. Number 1, pretty obvious, the strength of the wind. The stronger the wind, the bigger the waves. Number 2 is how long that wind or that storm sits over one area. And it takes up to 3 days to get maximum size, wave formation, maximum energy transfer into the water. So time is a factor. That's wind duration. And then fetch is the term that we use for the area over which the wind blows. Once the waves move out from underneath the storm, they're not going to be able to collect any more energy. And so the fetch is important. The larger the area covered, the bigger the waves we can make, because we have more opportunity or more area in which to transfer energy. And all of this plays into this diagram from your book, which is kind of interesting. It shows you that the largest waves that we see tend to form in the Southern Ocean, where we have those constant winds blowing from west to east. So we have very strong, consistent winds that allow the production of very large waves. Another important characteristic to note is that the waves are going to interfere with each other. We don't get just one single set of waves. So when different sets of waves interact, we can get crests from one set in the trough of another set. That's what we call destructive interference. It tends to level the water out. That's what we see in the middle here. We get smaller waves than we might otherwise expect. But what's more dangerous is the constructive interference. That is what happens when a crest aligns with a crest. So when crests from 2 or sometimes even 3 wave sets interfere constructively, you can get especially high crests and deep troughs, and you can actually violate our 1/7 limit. You can get waves that are taller than they should be, that last for a very short period of time. But if you happen to be in a ship that's affected by that, that's not very good. The other thing to note about wave interference is that the wave set will move on after it has interfered or been interfered with. So the interference is temporary. The waves do not go away. They're not permanently canceled out. Wave interference is a temporary effect. So, what happens as a wave approaches the shore? Well, this will be my teaser for the next video set. We'll start here.